So this is question number 3. It's from the 2015 AB exam. It's also one that appeared on the BC exam. This is the first non-calculator question. And what they say we have going on here is there's a girl jogging in a straight path from 0 to 40. The velocity that this girl had is given by a differentiable function v. We have values of v and the corresponding values of t measured in minutes indicated in the table up here, and velocity is being measured in meters per minute. Part A says use that in the table to estimate the value of v prime of 16, which would also be the approximation for her acceleration at 16. So we can't find that exactly, but what we can notice is that 16 sits smack dab between these two ordered pairs. So if we estimate the slope of a tangent line on the velocity graph, or the derivative value on a velocity graph, by using a secant line that bookends the point that we want to make our estimate at, we're going to have a pretty reasonable estimate as a result. So we're just going to do a slope calculation between these ordered pairs. It doesn't really ask for units or for an interpretation, but the units would be meters per minute, or meters per minute squared, and that would be her approximate acceleration at the t-value of 16. In part B, it gives us this integral, and it wants us to use correct units and explain what this means within the context of the problem. Well, if this integral did not have absolute values around velocity, when you integrate velocity, your result is going to be a number that tells you how much position has changed. But when you have the absolute values here, any changes in position that happened in the negative direction are made positive by the absolute values, and this integral turns into one that computes total distance traveled for us. And so the meaning of this integral is that it represents the total distance Johanna jogged from minute 0 to minute 40, and then the units would be meters, because units of v of t are meters per minute, units of dt are minutes. The minutes are going to cancel, and our result is measured in meters. And then it wants us to go on and estimate the value of this using a right-Riemann sum and 4 subintervals as indicated by the data in the table. So our 4 subintervals would go 0 to 12, 12 to 20, 20 to 24, 24 to 40. So we have a width of 12, a width of 8, a width of 4, and then a width of 16 for each of our subintervals. And then the heights are going to be indicated by the function value at the right endpoint of each subinterval. So the right endpoint of this subinterval is 12, so that's going to generate our first height. Right endpoint of this subinterval is 20, so this is going to generate our next height. This is not going to generate our next height because we don't want to do this calculation for v, we want to do it for the absolute value of v. So we're just going to change the sign of that to a positive whenever we use it within our sum. And then the height of our last rectangle is going to be 150 coming from the function value at the right endpoint there. So when you use those widths that we rattled off a couple minutes ago and the heights that we were just talking about, and make sure that you change the sign of that one value that was negative so that you continue to accumulate distance rather than subtracting off distance that was traveled in the negative direction, you're going to end up with needing to evaluate this. You don't have to do this on the AP exam, but if you wanted to carry out the arithmetic to figure out what the number of meters traveled actually was, you end up with 7,600. In part C, says another person, Bob's riding his bicycle along the same path. From 0 to 10, his velocity is modeled by this function. T is measured in minutes and b of t is measured in meters per minute. We want to find Bob's acceleration at t equals 5. So what you have to recognize is that acceleration is the rate of change of velocity, or the derivative of velocity. So since this is Bob's velocity function, we would need to take the derivative of this velocity function and then evaluate it at 5. So it's a pretty simple derivative, just a power rule, and then you're going to evaluate that at 5. And like we said earlier, you could leave your answer like this if you wanted to. We typically don't like to do that. So if you went ahead and did the arithmetic, you end up with 15 meters per minute squared for Bob's acceleration at t equals 5. And then the last piece of this, it's having us work with Bob a little bit more here. And it says that we want to find Bob's average velocity on the interval from 0 to 10. So if you know the formula for the average value of a function, you basically want to apply that formula to Bob's velocity function. And so we're going to do 1 over 10 minus 0 times the integral from 0 to 10 of Bob's velocity. And then it's just going to be a matter of using the fundamental theorem of calculus to find the value of this definite integral. And so when you do the antiderivative of this, you're looking at this result. This is going to simplify a little bit. You're going to get 2t cubed in the middle there. You want to put 10 in place of your t's. You want to put 0 in place of your t's and take a difference. So that's what I have indicated on this line here. And like we've said several times, it'd be fine to leave your answer like this on the AP exam. You would want to carry out the arithmetic if you wanted the numerical value for this result. So if you take a few minutes to carefully go through that, you should end up with 350 meters per minute for Bob's average velocity.